Hello and welcome to this talk on stream chemistry. Today we're going to study carbon. We've already covered a bit of nitrogen, phosphorus, and oxygen, and now we're going to deal with carbon. Carbon is a really important component of streams for a variety of reasons, not least of which because it's the substance that organisms build their bodies out of, but also because it's important in relation to pH, which we'll discuss today. That brings us back to this slide again. Today we're going to discuss what I'm classifying as another nutrient, but what is a component of streams. We're not going to discuss pH specifically today, but I want you to know that that's coming very, very shortly as we get into stream chemistry. So a number of objectives. Again, this is just a way to review if you've gotten the materials out of this lecture. This lecture is going to be a little bit shorter than the other lecture, but I wanted to set it apart because carbon is so different in some ways. Make sure that you can understand the complexity and describe the carbon cycle. One of the other things that's going to be really important is a theme again with this course is the interconnectedness of the aquatic and terrestrial system. Just look at the picture behind you. And finally, carbon cycle has become very, very important because it's so intimately tied to global climate change. And because of that, streams and lakes as well are really critical places where climate change is going to have large impacts and which are also going to feed back and produce different responses within climate change because of the way in which they're important to the larger carbon cycle. All right, so let's take a quick look at the carbon cycle in this simplified version. First thing you're going to notice is there's a lot of letters. Some of these are molecular formulas, some are abbreviations. Let's start with the molecular formulas first, and I'll dot them with red as I go through. CH4 is methane. To be clear, methane is, here I'll highlight it up here. Methane is not something you can smell. It is a very potent greenhouse gas, and it's always a gas at normal temperatures and pressures. If you take an oceanography course, you may learn something about fire ice or methane clathrates, which are frozen methane chunks in the bottom of the ocean. But for the purposes of stream ecology, it's always a gas. The other one that's up here, another molecular formula that's up here is CO2. Okay, and CO2 is literally just carbon and oxygen. It is the primary driver of climate change because it's the thing that's increasing fastest in the atmosphere. It is very, very good at trapping heat, and it is also really important for organisms because it is the source of carbon in the biosphere, because that's what plants and algae are actually pulling in from the atmosphere to produce their own biomass, and so ultimately what everything is dependent on. The other names I'm going to highlight now with a pen so it's a little bit easier to see. The other names on here are shorthand names. DIC, I recommend you write these down as we go. DIC is dissolved inorganic carbon. Okay, it's strongly related to CO2. It is not itself CO2, but you will see what that looks like. I should say it's primarily not CO2. CPOM is coarse particulate organic matter. Wherever you see OM, that's organic matter. What we mean by coarse, fine, dissolved, which I'll get to as I go through this list, will be obvious as we go through the lecture. FPOM is fine particulate organic matter, and DOM is dissolved organic material. The other one, a couple other things on here that are more obvious. There are things like organisms are a significant component of the carbon cycle, right? A lot of carbon is stored in organisms of numerous different types. And then in addition to that, I have this grab bag down here at the bottom, which is literally anything. There's just too many types of carbon for me to deal with to put into all different names. So for the purposes of that, storage can be any source. Storage can be recently laid down material, and so it can be things that you could potentially eat. For instance, a dead animal, right, lands on the ground. That is now becoming stored material in a sense, and it may be something you can actually consume. It could also be things like sediments and soils, which are organic rich at times or can be organic poor, but include a lot of carbon within them, and organisms are very happy to go about consuming them. Storage can also be things like methane or fossil fuels like oil, right? Those resources, you may think that humans are the only things that have used oil as to exploit for energy, but numerous organisms consume oil. In fact, an issue with things like frac pads, which extract fracking materials from the soil, is that they grow a lot of bacteria. So bacteria are very happily chomping away on those materials. All right, and what I want to show you now is to spend a little bit of time on this pathway. What you can see is that terrestrial material is going to be coming in very, very frequently, right? That's going to be entering streams. That's going to go through a pathway that's going to move organic material directly into the stream. CO2, on the other hand, is going to enter as a dissolved substance. That dissolved substance is going to be incorporated into things like phytoplankton. Now, on this particular graph, you'll see that I don't have phytoplankton, right? Phytoplankton would actually occur right here. Let me highlight it in green. Would actually occur right here. Oh, it's really hard to see, so I'll make it big. And really what they're going to do is they're going to provide this arrow from dissolved inorganic to fine particulate organic material. They are usually very small, and the trapping of that material by other organisms will contribute to fine particulate. If DIC happen to be laid down by plants in the water and then brought into the food web, then it would actually enter through CPOM. But it turns out, and we haven't talked about this yet, but we will as we go further in the course, that plants, aquatic plants, that being true aquatic plants, not aquatic plants in sort of the colloquial term of anything green that lives in the water, but true aquatic plants contribute very little to food webs. So when you go out and see lots of aquatic plants growing in a lake or in a river, there's not actually that much that's eating them directly. There's some, but it's pretty limited relative to things like phytoplankton. All right, so let's talk a little bit about what I mean by things like coarse particulate, fine particulate, dissolved inorganic. All of what you see here, well, let me highlight it. All of what you see here could probably be described as coarse particulate, okay? Leaves getting broken down into other material, so very large items that are easily visible with your eye. When that material gets broken down further into very small chunks that are fairly hard to see, and this is based on a size thing, but as a general rule, it's detectable with your eye alone. When they get broken down to the little pieces that have to be gathered, and say at about the cellular level, then you end up with what's fine particulate organic matter. Okay, and if you get even smaller than that, then we're going to deal with dissolved organic matter, so that DOM. This is a great example of what actually happens, right? So you can see that certain parts of a leaf will break down. This larger component of the leaf now is certainly CPOM, but the smaller bits that have been removed from it and that have now entered the food web would be FPOM at this point. Now we just looked at what CPOM looks like, and I wanted to show you what FPOM looks like. FPOM looks far more like what you're seeing in this stream here, where the material is small, but if you were to collect a lot of that water that's passing down in this stream and held it up, you would actually see very fine particulate in there. And that is what is actually making up what is fine particulate organic material. Fine particulate organic material here is coming out of a glacier. This is a classic glacial stream. You can see that this is a very different world of carbon cycling than we saw in the streams before, right? And so streams again are highly variable between different locations. If you zoom in, you can see that even more. So some streams will have huge amounts of carbon that may not be strongly tied to, say, organic material. They may be tied to material that is quite a bit older, right? These materials that are being washed out are often very, very old carbon sources. They can be weathered out of rocks or out of soils. So they were at one time plants or they were marine material, but they have since weathered away and they are now thousands of years old. So some streams, although we think of the carbon cycle as being intimately tied to plants, are also actually very intimately tied instead to rock bodies by contrast. And you can see here This surface here is highly variable in its wetting. Sometimes it would be submerged, sometimes it would not be submerged, sometimes it would be frozen, sometimes not. Right. All right, let's take a look at DOM. DOM is dissolved organic material. Dissolved organic material is what gives this water this nice dark color. Okay, so take a look here. Look at how brown this water is. Maybe I should use a color that you can actually see. That seems like the more obvious choice. Look at how brown this water is. Oh, it shows black. That's actually fine. Brown this water is, right? But you can easily still see the bottom. But clearly there's a lot of material floating in that water. And it turns out that that's a lot of organic carbon, okay? If you were to take that water and you were to hold it up to the light and squint really hard, you wouldn't see anything. If you were to put it under a microscope and you would just squint at it really hard, you would see nothing. If you were to dry off all the water, you would get sort of a thick brownish sludge at the bottom. And that would be organic material, right? So what's happening? Well, it turns out these are literal molecules. You can't see them. They're so small at this point. They've been processed for so long. And the reason that they exist for a long time is because they're hard to break down. They are actually quite difficult by this point for organisms to rip into. And so dissolved organic material will last for a long time. When you look at this stream, you can also detect that that brownish color looks a lot like tea or maybe very weak coffee, right? And that should not surprise you. I'm not concerned that you know these different materials, but I want you to appreciate that what makes up DOM are long chains of carbon, and that it's going to be impacted by things like oxygen again. As I warned you before, oxygen is really important to reactions on the surface of the Earth, and it being present or not being present will have hugely important differences in the pathways that organisms can use to maintain metabolic function. So oxygen is really critical at all stages. But what you can see here is at the top, look at this, it's a very simple compound, right? Just some carboxylic acid and the long chains of carbon, a couple of oxygens hanging out on the end, and that's basically it. And those variability in those lengths will help change the color, right? In addition to that, there are these ones that look a lot like what we call steroids. Not entirely the same thing, but you can see a lot of six-membered carbon rings stacked up together with lots of double bonds in them. So there's a lot of ways in which terrestrial carbon, or I should say carbon, dissolved organic carbon, can look in a stream. And you can see that those are often long chains and occasionally large numbers of rings stacked together, which help give them those colors. And as I mentioned before, it shouldn't surprise you that teas and coffees look these different colors. That's really unsurprising. A lot of dissolved organic material is leached from leaves, right, from terrestrial sources. So when you heat water and put it over a leaf, what you're doing is just speeding up the process of leaching out dissolved organic materials, and you're extracting those materials for you to drink. A couple of questions here I'm going to ask, and you may want to pause and think about them and then see if you're right. Why is green tea and black tea different in color? What's different about those teas? Why are teas and coffees bitter? Why is one of the flavors that is often associated with these bitterness? Okay. And then why are they 0 calories? Right, so I just talked about them being long change of carbon. Certainly there's energy packed away in those. All right, so let's take those slowly as we look at this. Colors in green tea and black tea and coffee. Green teas are literally just dried tea leaves. They are plucked from the plant and they are dried. And that picture on the left bottom shows you a good example of that. They actually are green. So these are relatively recently fallen leaves in a sense. That's what would happen in a stream. The water moves through them and extracts these dissolved organic materials that are often less broken down. So they will have a sort of sharper, tangier flavor. All right, and they tend to be that greenish color. Black teas, on the other hand, are fermented. So bacteria have actually gone about doing a lot of work for you. And as a result, they leave behind compounds that are even more difficult to extract resources from. And that's why you get real bitterness associated with them as well. But in addition to that, the color changes to this much darker tone. And you can actually, if you're interested in why, you can go look up the molecular structures that are changing to change the color here, but understand that there's processing going on. If you compare that, say, to a coffee bean, right? You say, oh, a coffee bean. What tell me about that? Well, coffee, if you've ever seen coffee harvested and brought to a coffee cellar, is actually a green bean that if you extracted materials from would be very, very poor tasting coffee, the really awful coffee. So what you actually do is very similar to what the bacteria do in a fermentation with tea is you help speed up the process of breaking down coffee compounds by heating the coffee beans to very high levels, right? And you burn them in effect. Now, if you're going to things like Starbucks or Charbucks, as you might want to call it, where they just literally scorch the bean, they like set it on fire and then they serve you cruddy coffee and pour bunches of different sugary syrups on it. Yes, that's truly burning the bean. But a good coffee dealer will actually cook the beans such that they help start the process of breaking down those compounds. And you get a huge range of those compounds, right? Because these beans have been broken down. But you get a lot of different kinds because the beans are all getting to slightly different temperatures. Even within the own bean, they're getting to different temperatures, and so different compounds are present all throughout the bean. And then you extract those resources by passing very hot water over them in one pass. You won't do it again because you're going to get the vast majority of those materials that are water soluble in the first go, and then you drink it. So you're actually sort of mimicking the process of fermentation to a degree by helping to accelerate the breakdown of those processes. Lastly, why are teas and coffees 0 calories? They are in fact very low in calories. They probably are very close to 0. It turns out it's very difficult for your body to extract resources from them. This is a perennial problem with dissolved organic material. Dissolved organic material is just hard to extract material from. These long carbon trains, even though they have lots of energy in them, are actually really resistant to degradation in the same way that things like cellulose and ligand are hard to break down. Even though you might be in a forest, right, and there is energy all around you in the form of, let's say, trees, right, tree bark everywhere, actual woody material everywhere, you could still starve to death. And that's somewhat crazy when you think about the vast amount of energy that is stored in, say, the woody material of trees, but you can't extract that energy from it. And so it's of no use to you, right? It doesn't help power the system that you need. So in the same way, coffees and teas have lots of these compounds in them that give them lots of very strong flavors, which are very nice to enjoy, right? The bitterness comes in many levels. It's not like all tea is horribly bitter. It's that they come in many different kinds of flavors and sensations, which is nice. And that results in you enjoying it, but they contribute very, very little to your metabolic pathways. And as a reminder, this is not real coffee or tea. Okay, this is a flavored sugar drink, which is fine if you like flavored sugar drinks, but don't tell me that coffees and teas and relationships to stream waters are similar don't make sense to you because you have your unicorn Starbucks Frappuccino. The other thing that's important to keep in mind here is that there is this continuum of change. So high in the headwaters, there's going to be lots of opportunity for coarse particulate organic matter to be entered into streams. Because just like with tea, it takes time for bacteria to attack and break down compounds, coarse particulate is going to be common in headwaters, but dissolved organic material is going to be common as you move out towards these larger 5th, 6th, 7th, 8th order rivers, right? So that's where there's going to have been time and lots of bacteria working away to nibble on that coarse particulate to make DOM. And by the time it's DOM, the process of breakdown is going to be very, very, very slow. And so we're not going to talk a lot about river continuum now, but I want you to appreciate that the carbon cycle changes spatially across the river. In some areas, some components of the carbon cycle are common. In other areas, other components of the carbon cycle are common. All right. There is what we call these spirals that appear. So as material moves through the systems, we're going to spend more time on that. But really what it's showing you is that that carbon cycle is is a transient process. It's moving down and with the river, and it's changing across the length of that river. This change across the length of the river is going to have profound impacts on the organisms that live in it, because some elements of the carbon cycle are going to produce compounds that are more common in certain areas, and some are going to be more common in other areas, and organisms dependent on one or the other are going to be more likely to be found in only certain areas because that's where they can get that material. Right? If you want to get lots of coarse particulate organic matter, you should not be down where the river gets very, very wide. You probably want to be fairly high up in the headwaters. In addition to that, so that's ways in which organisms need carbon to actually eat to live. Lots of organisms depend on carbon for a variety of things. Of course, plants and phytoplankton depend on it for dissolved inorganic carbon, which is CO2 that they need to actually make the carbon compounds they depend on. But other organisms use it to build their bodies. So there's a lot of mollusks out there. Mollusks are very, very common, and mollusks are not the only thing that use carbon. And they use it actually both to feed themselves, right? So they pull material out of the water column, particulate of all kinds, but they also need it to actually construct the houses in which they live, right? Their own shells are made out of this. These are freshwater, what we call mussels. I'm putting it in quotes. They're not terribly closely related to what people traditionally think of as mussels when they go out to the grocery store to buy them, those little blue or sort of bluish green things that you would buy. Those are a very different group from these. But these mussels are very, very cool. They're endemic to North America. They evolved when North America was an ocean, and when the ocean got sealed off, they became highly modified to live in freshwater systems. They have a very cool parasitic phase within their life cycle, and there's huge numbers of species. Turns out as well that these have been hugely overharvested, and their numbers were very, 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 very high even within the past 100 years, but have since declined and bottomed out, and a number of them have already gone extinct. And they were used primarily for buttons. So if you have buttons on a shirt that say were before the plastic revolution, so if your grandparents provide you a inheritance of any kind and you get a shirt from them with buttons on it, it's actually very common that it was probably made from mussels that were collected in North America. It was very easy to stamp out buttons from these. In addition to that, other organisms are also really important to the ways that carbon moves through streams. And when small things are really abundant, they can have really profound impacts on the carbon cycle. So for instance, black fly larvae, which is what you're looking at here, actually eat and produce so many fecal pellets from the particulate that they collect in the water column that they substantially change stream budget carbon cycles. So black flies are really important to the way in which energy moves around in streams because they change what's common in the stream. They themselves alone, no other organism, right? So if you don't know what a black fly is, they're these guys. They're blood-sucking flies. The problem is, unlike a mosquito that bites and you usually can't feel it, or it's a very temporary bite, black flies cut and lap, so they have mouth parts that slice open the skin and then they lap up blood very quickly. They have evolved to get hit very hard and survive, so they're fairly robust bodied, and they're very, very persistent. So females looking for a blood meal will not give up. They will come for you. They're relatively small, but they're very, very common in a number of flowing waters. And the larvae here on the right, you can see, are out there collecting some carbon for their own bodies. One of the other things we need to talk about is this thing called the microbial loop. And I know that we've actually already covered this to a degree, right? Especially if you were looking at the carbon cycle closely when I introduced it. But take a look here. I'm going to start with the process again, just as we did for the teas and the coffees. You can see that things like leaching of DOM, right, from leaves contributes substantially to this carbon pool. And that carbon pool can actually go in the direction from DOM to POM, right? So how does that actually occur? Well, it turns out that bacteria and fungi, as they are eating this DOM, will start to accumulate together, right? They may form biofilms, they may just get stuck together, and they may, as a result, produce POM. Sometimes that POM is exported out of the stream, right? It's getting washed away. But sometimes it's also eaten by other things, right? Sometimes it gets sunk into the bottom of the water and gets buried, and sometimes, of course, it gets respired and then it gets released to the air as CO2. There's a lot of ways in which these bacteria and viruses are moving dissolved organic material into a variety of different pathways. In addition to that, bacteria and viruses can be converted back into or bacteria and fungi can be converted back into DOM by what I just gave away, which is things like viruses, it turns out, are incredibly important for this. So one of the most important things on the surface of the earth is viruses because they help to modify and break down bacteria, and they release organic material into the water column very, very frequently. So bacteria are constantly being consumed by viruses. Consumed, I guess, is not the right word, utilized by viruses to produce more viruses and broken up. And if you remember back to any early biology class where we talk about viruses, some of those simple processes of viruses causing bacteria to lyse produce lots of material being sort of sprayed out into the water column. And this happens on the order of trillions of times a day, right, at any location, because there's so many bacteria and so many viruses. In addition to that, bacteria are also consumed by a wide range of things, including things like protists, which are eukaryotes or cells with nuclei. And protists are very happily spinning around, nibbling away on the bacteria. So if you are bacteria and you see something like this guy shooting around, right, that's really terrifying because this guy spends his entire day doing nothing but eating bacteria, and that's converting POM back into POM within the body of this protist, but also it's producing DOM, right, and CO2, which is being released into the water column. So it's converting this particulate back into a respiratory, into an atmospheric phase, and it's also converting it, some of it, into a phase which may be consumed by other organisms, or may they get buried at some point, or that at least temporarily is POM swimming around in the water column. I took this image from the reading because it's a really wonderful example of the variability of DOM in streams. Take a look at all these different streams up here at the top in these what are effectively milk jars. What you can see is that the color is all different, and they look often like a maple syrupy color. What does that tell you about things like maple syrup, right? So if you've ever seen maple syrup production, or you have ever had maple syrup, not the fake stuff you buy that's flavored like maple syrup, but real maple syrup, you'll know that there is sugar in there, but there's also these very astringent compounds, and that's really that DOM kicking in. You'll also know, if you've had maple syrup, that there's lots of different kinds of maple syrup, and it really depends on what kind of trees you're tapping to get what flavor. And that suggests exactly the kind of thing that you would anticipate for a stream. It's going to be really important what kind of environment the stream runs through, what kind of DOM is available, because different terrestrial plants will produce very, very different DOMs. So for instance, take a look at this tulip tree material, right? Look at how dark that is, so substantially dark. Compare that to eastern white pine, a very, very, very light material, right? And these colors are going to be reflective of different molecular species, and different molecular species are going to be easier or harder to break down, which is going to change the process within those streams themselves. All right, so this is a really great example visually to see that not all streams are the same. Even when we talk about things like dissolved organic material and material moving through things like a microbial web and entering or exiting from in a gaseous phase, even that is going to vary depending on what stream you're in, and it may change substantially, right? Clearly, this person that collected all these in what's probably a single day did not go to, let's say, streams that were 20 hours apart, right? They didn't drive all over the world. They drove to a very narrow and small area of location, and then they sampled at a bunch of different spots, right? And so all of this occurred in a very small amount of area, right? And so these are the kind of things that organisms, even on small spatial scales, are going to deal with all the time. All right, and so next up we'll deal with just a little more stream chemistry because we have a few more things to cover, and then we'll be done with our stream chemistry component.